Okay, so hello everybody. Uh, I was honored to chair this session number 4. So I would like to invite the first presenter, Janka Borzova, with a contribution named Exploring the Upper and Sugano Integral and its Role in Scientometrics.
Good afternoon. Thank you for the introduction and thank you for being here. In this talk, I focus on the upper n Sugano integral, which extends the classical Sugano integral and was proposed by Wojciech and co-authors with some scientometric applications in mind. In this talk, I show that its computation can be understood as a midpoint problem. And finally, I introduce the Hirsch-Sugeno operator that can be understood as a unifying framework for many scientometric indices. So let me start with level measures. They naturally appear when we study the Sugeno integral. A level measure is a function, as shown in the figure, that is non-negative, non-increasing, and defined on the zero infinity. Of course, we would restrict it to 0, 1, but for our purposes, we will keep it on zero infinity. Depending on how this function behaves, Citescu distinguished a few essentially cases. Some of them are quite trivial. That is, a function is identically 0 or identically infinity on the open interval 0 infinity, and therefore uninteresting from the integrational point of view. Another ones are interesting situations where the function changes its value from infinity to 0 at some point between 0 and infinity. That is finitely non-trivial function. And infinitely non-trivial functions achieve finite values. And these functions may or may not interact with the diagonal. And this interaction leads us to a notion of a midpoint. Simply said, a midpoint is a point where the function changes its position with respect to a diagonal. And as we see on the left, it's above it, and on the right, it's below it. This example shows idea of midpoint. So if we compute the Sugeno integral, we don't have to use the classical definition, this one, via the supremum over T from 0 infinity. But it's enough to find a point where the level measure changes its position with respect to a diagonal, as it's shown in this figure. In this example, it's 2/3, which is the value of the Sugeno integral. We were inspired by this idea and we tried to apply it in the context of the upper n Sugeno integral. But before coming back to midpoints, I would like to introduce the definition of the upper n Sugeno integral. So as I said, it was introduced by Wojciech and co-authors, and the idea is simple. Instead of taking the supremum only once, we iterate the same construction. At each level, we combine the current level T with the previous value of the iterated Sugeno integral using an admissible fusion map. An admissible fusion map is a map which is non-decreasing and which satisfies boundary condition, which ensures that combining with zero doesn't increase the value. Uh, After introducing this construction, a very natural question arises: does this construction always produce something new? This question was the first one which we solved in our paper. So we found that if the second step coincides with the classical Sugano integral, then another iterations don't change the value. And moreover, we identified a broad class of fusion maps for which the upper end Sugano integral coincides with the classical Sugano integral. That is, if we take an admissible map which lies between the minimum and maximum, this situation occurs. And now I would like to return to midpoint. So a midpoint or midpoint in the context of the upper end Sugano integral was quite simple, natural idea. We fixed an admissible fusion map and the positive parameter p, and we say that the function h has a midpoint with respect to an admissible fusion map and the parameter p if for all values greater than x0, the graph of h lies below x fused with p, and for values smaller than x0, the graph of h lies above x fused with p. Uh, if the graphs of h and x fused with p meet at the same point, then we say that a midpoint is a strict midpoint. And now we can see a quite technical result, but important. It states that if a midpoint exists, then it's unique. And the second result is T1. It states that under some assumptions on admissible fusion maps, namely right continuity at the point 0p, increasingness in the first variable, unboundness, left annihilator at 0, and finiteness preservation. Function h has a midpoint with respect to an admissible fusion map and a parameter p if and only if it is non-trivial, that is, it's neither identically zero nor identically infinity on the open interval 0 infinity. Here we can see one of our structural results, which states that the upper end Sugano integral behaves in a similar way to the Sugano integral. Namely, if the level measure has a midpoint with respect to an admissible fusion map and the value of the iterated Sugano integral, then the upper end Sugano integral can be obtained by combining this midpoint with the previous value of the upper end Sugano integral, this formula here. And now I would like to say something about scientometric applications in this context. As I said, the upper end Sugano integral was proposed by Borcek and his co-authors in order to overcome some limitations of the Hirsch index and extend the approach of Estier and Gagalowski. And based on this idea, we introduced the Hirsch-Sugano operator, which combines the classical Hirsch index here with the construction of the upper end Sugano integral. So in this definition, we work with two vectors. The first one is the input vector f, whose components represent the numbers of citations of each scientist publication, which are ordered in a non-increasing order. And then we have an input vector G, which can represent, for example, the vector f divided by a scaling parameter, or it can represent a vector whose components are the numbers of citations divided by, for example, the numbers of co-authors or the age of each publication, and so on. And here we have an admissible fusion map, an arbitrary non-additive measure. So this operator can be viewed as the classical Sugano integral of a suitably transformed vector, namely this one, G with star, and its value doesn't depend on how the ties of the input data are ordered, because of the monotonicity of the admissible fusion map. Further, we showed that it retains classical monotonicity properties. So if the function g increases or the measure increases, then this operator doesn't decrease. It also retains classical lattice operations, minimum and maximum. Next, for specific choices of admissible fusion maps, we derived these explicit formulas. And finally, if we consider the input vector G, which coincides with the vector F, and the counting measure, and an admissible fusion map with this property, then the Hirsch-Sugano operator reduces to the classical Hirsch index. This Hirsch-Sugano operator covers many symptometric indices. For example, the first one is H alpha index, where it's enough to take minimum admissible map, counting measure, and vector G defined as further lower to H index. Here we have addition, counting measure, and the input vectors, which are the same. And finally, the Kozmolsky, the generalized Kozmolsky index, where we have this admissible fusion map, the same input vectors, and again, the counting measure. On this slide, I summarize these examples. Of course, they aren't exhaustive because many other indices are covered by this framework. But what I would like to say that this Hirsch-Sugano operator covers, on the one hand, indices which value is independent of the classical Hirsch index, and on the other hand, the indices which value depends on the classical Hirsch index as the lower to H index. So I think that's all from my side. Thank you for your attention.
Okay, so now we have time for some questions or remarks, comments. Anybody? No questions? Okay, so maybe we can continue with the next speaker. Matusz Jubek is the next speaker with contribution entitled Modification Inequalities. So, Matusz.
Okay, so thank you for introduction. Today, my speak will be about, as it was said, modifying decomposition integrals by using inequalities. First, I will go over the definition of decomposition integral within the context of this speak. Then I will introduce the generalization and provide some illustrative example, which will show why such a generalization should be considered. So decomposition integrals were introduced by Evan and Lehrer in 2014, and they are a generalization of a lot of known type of integrals, such as Lebesgue integral, Choquet integral, concave, Gilchrist, Pan, etc. And they are based on decomposition of the integrand into a combination of indicators. Let's set up what we are working with. We are working with a finite space X. In some other work, infinite space is also considered, but within this talk, we will only consider finite space. Then we will work with some non-negative functions, which will form a class all possible such functions. Then we will work with a monotone measure, which is a mapping from power state of the finite space to a positive value such that the value for empty set is always 0, and it's non-decreasing with respect to set inclusion. And of course, this will also form a class of possible monotone measures. Next, we will work with a collection, which is a non-empty subset of the power set that doesn't include the empty set. And we will use these collections to form a decompositions of the positive functions. But we will only consider positive, only indicators of the sets from collection. And also we will consider positive coefficients for them, which is natural because we are working with positive functions. And again, class of all collections is denoted by the. Next, we'll work with decomposition system, which is a non-empty set of collections, and is posing a set of alternatives of possible decompositions for our functions. And again, they form a class of all possible decomposition systems. To every decomposition, we will map the value given by the measure we defined before. So how it works, we are working with a function, a monotone measure, and a decomposition system. We'll go over all sub-decompositions of the function f with respect to the collections from the decomposition system, and we will find the greatest value with respect to the monotone measure. And then among all collections from the decomposition system, we will again find the greater value of those, which gives us the decomposition integral, which to define in a more nice comprehensive way, defined here. So it's an operator from which gives to every function from the set of all possible positive functions value from 0 to infinity, so positive value, and it's given by this formula. Okay, for some examples, it is easy to reconstruct all of these already known types of integrals. When we consider, for example, a finite set which only contains 3 values, 1, 2, 3, if we take set of singletons or collection of singletons from our decomposition system, then we obtain Lebesgue integral. If we choose chains, which are subsets of the power set, we obtain Choquet integral. If we take the entire power set without the concave integral, Gilchrist integral. If we consider singletons from the power set, but collection of singletons of or collection containing singleton collection sets of power from power set. Yeah, that's the right way. Sorry. or pan integral when we have a partition of X, or the PC integral introduced by our dear colleague Andrea Stupnilova. If we consider such sets that are either embedded into each other, so the intersection is one of them, or they are disjunctive. For an illustrative example that we will come back later, consider a company with a set of employees denoted by omega. Then the mapping F represents the maximum number of hours that an employee can work for a day. The measure represents the productivity of the employees or the group of employees. And the decomposition system represents alternative working schedules for them. So then the value of the decomposition integral would represent the maximal productivity of the company for given functions of the maximum number of hours. For more specific example, let's consider a small company with only 3 employees, worker 1 and worker 2, and 1 manager. So the omega is this simple set. And let's set the functions as constants, which are unknown, but they are both positive real numbers. And let's define the measure in the following way. Of course, if no one is working, we have 0 productivity. If only the manager is working, we have also 0 productivity. Workers have some productivity, but it's not additive. So that if they work together, they only increase a little. And only worker 1 has an increased productivity if he's working with a manager. And finally, if they are working all 3 together, they have the greatest productivity. Now, to add some additional condition, let's assume that worker 2 is in training and he can only work if the manager is also working. Then we can consider such decomposition system with only one collection, which always contains either worker 2 with the manager, or it doesn't include him at all. Then this problem inputted in as a decomposition integral leads to a problem of linear programming, and it can be shown that it leads to this function, which is piecewise defined depending on how we choose the parameters a and b. But let me point that it's not bounded at all. So potentially it's infinite. Now we are going to the part of introducing the modification. So the problem is, as illustrated, that it's easy to obtain such a solution that it's not real life obtainable. So we should introduce some additional constraints to keep it grounded in real life. So we will introduce the additional boundaries in form of linear inequalities. So under constraint, we will denote such an inequality in this way. The notion might be strange, but we will show later that it's the same as we used before, where these parameters and the right side are some arbitrary real numbers. Unlike before, with the parameters alpha, now they can be negative as well. A constraint is homogeneous only if the right side gamma is 0. And again, a set of all possible constraints forms a system. Now, here's the modification. So we are defining the integral not only with respect to the measure and the decomposition system, but also to the system of constraints. And the way we are doing it, that this part stays the same as in the original definition, but here are the additional boundaries with the same notion as before, that for every indicator function we can map the value alpha from the original definition. And again, alpha stays some positive coefficient. Now, these integrals have managed to satisfy all the original properties that if the input function is always 0, then the result is again 0. If and then they are non-decreasing with respect not only the function we input, but also to the measure we use. And but however, unlike the original integrals, now they are not homogeneous in general, but only if all constraints used are homogeneous. Let's get back to our example with a company with 2 workers, one in training, the same measure as before. But now let's input the new constraint that the worker in training must work at least 2 hours a day. So we introduce constraint in this form with negative coefficient in order for it to be in the same pattern as we introduced. And it can be shown that, again, it leads to a linear programming problem with some additional boundaries, unlike before, that the results in the same function or function with same results as before, but the boundaries are changed. You can see that on this visualization that it's not possible to define A and B because worker in training must always work with a manager under the value of 2. With the same approach, we can introduce another nice constraint that all workers should work maximal 8 hours a day, which would be nice for everyone. We can define them in such a way. And again, it leads to a linear problem which can be solved. Now, the solution is quite more complex than before, but the important thing is that it's bounded by 80. So if we take the maximum productivity times the number of hours, we get the upper boundary, which doesn't depend on how we choose the values A and B. And of course, we can choose to combine these constraints into some larger set of constraints, and then the result will accomplish both constraints. So it's bounded by 80, and we cannot choose values lower than 2. So for conclusion, we introduce a definition of constraint decomposition integrals. We demonstrated advantages of such modification on a not real life, but illustrative example. And for future research, we would like to try to use some nonlinear constraints, which leads to different types of optimization problems. Further generalize the definition by replacing characteristic functions to fuzzy membership functions, or even some modified type of fuzzy sets, and also further study property of such integrals. That will be all for me. Thanks for your attention.
Presenting these results. So are there any questions from the audience? Okay, so we have a question.
Hello, Tomek here. So thanks for the presentation. You showed that the topic of your presentation was modification of the composition integrals. And we already have seen that people are often using some of the modification of integrals. For example, the Shocket integral lastly presented So do you think that you would be able to decomposite the modification of the, for example, socket integrals in the way that you have presented here?
No, I think I don't see the problem. Why not?
Yeah, maybe this would be an idea for some future research. Okay, thanks.
Thank you.
Thank you. Any other questions?
Have you considered also super decomposition integrals with inequalities?
Just not yet.
Okay, this is only continuation of the proposal.
This is the future of this. So maybe we'll work on that later. Okay, any other questions? I think. Okay, so thanks again, Matusz. Okay, the next topic is time-dependent fuzzy measures of Fateme Kuchakinejad with collaboration with Professor Messier. The stage is yours.
Okay, hello everybody. I'm Fateme. I would like to speak about time-dependent fuzzy measures, a joint study with Professor Messier. Okay, first of all, I would like to just take a look on some known definitions. The definition of aggregation function, which is a mapping that is non-decreasing and satisfy two boundary conditions. Here we show the aggregation functions with bold letters. Also, we considered a finite set of n elements from natural numbers, say capital N, which is a finite set, and depending on the application, it can be, for example, players in a game or criteria in a multi-criteria decision problem, and etc. Also, fuzzy measure, it's a set function satisfying boundary conditions and monotonicity. We here show the set of all fuzzy measures by this notation. Okay. Why we need time-dependent fuzzy measures? If you just consider one process in which you repeatedly use fuzzy measures in every step, okay, until now, naturally, we consider one fuzzy measure and work by that fuzzy measure. What if we want to consider for every step, depending on a new fuzzy measure? If we just define the fuzzy measure for every t as a new fuzzy measure, which is like a sequence of fuzzy measures depending on t, we call it a memory-less time-dependent fuzzy measure. It means that it doesn't depend on the previous steps. So it's easy to use, but no learning from the previous steps. But if we want to also learn from the previous steps, we would like to introduce p-dynamical time-dependent fuzzy measures. This p-dynamical time-dependent fuzzy measure use the previous measures, and also we consider some part to have influence and control on our dynamical time-dependent fuzzy measure. Okay, first of all, we introduce this definition for memoryless time-dependent. A memoryless time-dependent fuzzy measure, for short here, we call it just memoryless fuzzy measure. It's a family of fuzzy measures we show here with this notation, and the T is from this set. Okay, it's infinite, but maybe for some practical usage, we can just consider it finite as we need. Also, every measure from here is monotone, and also it's satisfying boundary conditions. So we will have a sequence of measures. one can consider sometimes for some t the equal measure, but it depends on you. And if you consider all measures equal, it will be just a normal fuzzy measure. We show this set of memoryless fuzzy measures by this notation. Okay, one example. Here we consider n the set of two elements and the power set. And we defined for every set, as you can see, different formulas. Naturally, we need to have measure of the n, 1, and empty set 0 to have fuzzy measure and have that boundary conditions. Obviously, here, this sequence is memoryless fuzzy measure, also probability measure. As another example, if we consider the initial measure by this formula, and for any other t, this formula, we will have again a memoryless fuzzy measure, and also it is a symmetric fuzzy measure. Okay, as you can see, it's easy to construct and use, but as I told you, for memoryless fuzzy measure, we can't use and learn from the previous measures. And if we want to have this learning, we will have this p-dynamical fuzzy measure. For p-dynamical fuzzy measure, we need some function which let us to control and manipulate the result. We call this function as influent function. This influent function is from power set to unit interval. Naturally, it doesn't need to have any property. But if we want to have some properties, for example, if we want to have the properties of fuzzy measures, we have to accept some properties of fuzzy measures on this I. Also, if we want, for example, to have probability measure, we have to accept the properties of probability measure. Okay, this is influent function, and now the main definition. B time dependent fuzzy measure with memory. Here we call it for short B dynamical fuzzy measure is a sequence of fuzzy measures. As you can see, it depends on T, and for every time, every step, we have a fuzzy measure depends on T. But how can we compute this measure here by this formula? Look at this formula. Here we have B as a binary aggregation function. Measure on a step T minus 1, which is from the previous step, and also this influent function. T is again from this set, and as I told you before, we can consider it finite if it is needed. We show the set of all B dynamical fuzzy measures by this notation. Okay. Continuing, I would like to mention some points. As you can see here, B is constant depend on T. But one can also consider B as a time-dependent aggregation function, which is changed for every step. Also, as you can see here, we have just the last previous step. One can consider here a previous measures. So if you want to use K previous measures, we have to accept to use K plus binary aggregation function B. And the formula can be like this. And if we, as I told you, consider B also time dependent, it can be like B indexed by T. But here we consider the simplest time-dependent approach related to fixed K, which is 1, and B is not depend on T. Okay, this B dynamical fuzzy measure is monotone, and it satisfies the boundary conditions. Here we want to speak about convergency. When we speak about a sequence and process, naturally, first of all, we ask ourselves, is it convergent? Yes. Here, by these conditions, we will have convergency. If B is continuous and Lipschitz continuous with respect to the first coordinate, and also if I is converges to some limit, say I, then this sequence of fuzzy measure will be convergence too. We are trying to relax the conditions of the theorem or have some other different condition for convergency. Okay, as I told you, one very important part of dynamical fuzzy measure is this influent function. Okay, we can have any kind of fuzzy measure for this influent function. For practical use here, we just offer a definition and a way of computing I. One can consider this definition or any other definition for I. If we consider G as a non-negative time-dependent data function and normalize this G by this formula, then by summation of F for every subset of A, we can define I. So from G, we will have F, and then we will have I. So in this case, we can compute I. Okay, to show the result, we can have one example. As we consider N, the initial measure is equal to initial influent function. And we defined and determined G for T for 0, 1, and 2. First, we consider B as minimum. This minimum and this aggregation function is determined by decision maker from the initial step. As you can see by the previous definitions, we easily computed the measures I, and also for steps for T1 and T equal to 2, we computed the measures. And naturally, as we need, and it should be like this, measure of N is equal to 1. Just consider these three numbers. Later, we will speak about these three numbers again in the next slide. Here, we choose product for aggregation function instead of a minimum. Again, we proceed for those from those definitions, and we have this result. These blue ones are this result from the minimum. And if you compare this result, you can see how the initial aggregation function that we choose for the process can affect the result. So it's very important to choose appropriate aggregation function for our practical problem. Okay, here we speak about some very special cases. If we have an influent function, a constant function depends on T. It means that I is always the same for all T. And if B is associative, then we can have the formula of B-dynamical aggregation, B-dynamical fuzzy measure like this. So it depends on just the initial measure and that constant I with respect to T. Also, if I is not just a constant function with respect to T, but also is a constant number, and that number is the neutral element of B, then all measures for all T will be the same as the initial measure. And if that A is the annihilator of the B, then all measures for all subset of A will be that constant number. So when we want to start and choose I, it's very important to consider this situation, these two, to avoid the trivial cases. Okay, here we considered a special aggregation function, say a weighted arithmetic mean, to show some result for this special case. We call this special case here dynamical fuzzy measure. And you can see the formula here. We have alpha, and alpha act as a memory parameter. With this parameter, we can manipulate and control the memory. When we consider alpha bigger, the memory will affect the result more. And when we consider alpha smaller, the effect of previous step will be less. So we can control it. And if we consider alpha equal to 0, you can see this formula will be equal to I. So it's kind of memoryless. It can be the same, it can be the first definition we gave for memoryless time-dependent fuzzy measure. And if we consider alpha equal to 1, all measures for all steps will be the initial measure. So these two types for alpha 0 and alpha equal to 1 are some trivial cases. So we will consider just alpha between 0 and 1 to avoid the trivial cases. Here, another example for this special case here, we consider alpha 0.7. So somehow we really want to have a more effect of memory. By the given definitions, we computed the mu for the subset, this singleton 1 and 2, and n as it should be is 1. Just please keep it in your mind. This example later, we will come back to this example, and we will continue not just for 1, also for other steps. Okay, this theorem is about Lipschitz continuity of measure M for that dynamical fuzzy measure. If I is Lipschitz continuous, also the initial measure is Lipschitz continuous, then we will have the dynamical fuzzy measure Lipschitz continuous with this constant. We use this theorem to prove this one. And again, we would like to know about the convergency. If I is a convergent sequence, then in particular, this sequence of measures will be again convergent. So for this kind of this a special case of bidynamical fuzzy measure, we have a more relaxed condition for convergency. Okay, now we want to show this theorem, how it works with this example. This example is related to the last example I told you. We will go back again to that example. As you can see, I, for every set, shows some kind of convergence. You can see when we go to other steps, it shows some kind of convergency. And for example, you. Yes, as I said, you can see a kind of convergency in these numbers. And again, it continues this convergency. And after step 9, it's somehow even constant number. So as we mentioned before, when we have convergency for the sequence of I, we will have convergency also for measures. And you can see the convergency on the sequence of measures. And this corollary came from the last theorem. In the last theorem, we said that if I is convergent, then mid will be convergent. But here, if we consider I and depending on constant with respect to t, then naturally the sequence of our measure will be convergent, and this convergency will that I. So we will get that I finally. Okay, for further research, as I mentioned before, one can consider or ignore some time dependency in some elements. For example, you can consider B time dependent, this I time dependent or no. And also you may consider here, instead of one measure, last measure, you can consider K last measure. And also considering time-dependent fuzzy measure in any measure-based aggregation function, for example, Sugano, Schuket integral, or etc., it can be a fascinating field of study. And some references, and thank you for your attention.
So thank you, Fateme, for this presentation. Are there any questions, remarks, or comments regarding this presentation? Martin?
Um, you can change this B and also I. Do you really need to change both? Is it not sufficient to have?
I think it depends on
Yeah.
purpose. If we want to have, for example, more information, not from the previous steps, but from this I to have more control, for every step we can consider I time dependent, or maybe we can consider is I constant respect to t.
Yes, but you have time-dependent I, and you may have also time-dependent B.
Yes.
So if you incorporate somehow this I into B, is it not sufficient?
You mean if we consider it depends on t, it's not needed to consider it as the time dependence, you mean?
This B can be somehow defined using I. And then you, it's just my idea, I didn't try it, but maybe you don't need such so many variables or so many functions.
The answer is coming from the...
I was not intending to do it. Because I don't understand what Martin wants. A is set, standard classical set. A. And I is fuzzy measure. And of course, this mu t minus 1 is again fuzzy measure, and B is aggregation function. So what's the problem? B is binary aggregation function, and there are possible several generalizations, but Fatema just told that she will consider this simplest case. So of course, several generalizations and so are possible, and surely she will work on.
As Sun Martin say that if we consider I B time dependent, it's not needed to consider I time dependent. But I think no. Because for every step, this B will compute these both, aggregate both. And if I change, definitely B will be changed too. It's another story.
Okay.
I think it's not bad to discuss with Martin then.
Okay, later.
Okay, so we have one more comment.
You never know where to decide that's very nice.
Yeah.
Thank you. As usual, in a generalization, there are many parameters or even functions, and it's easy to refer to experts, which I have never met in my life, who will give those values. So when I hear dynamical system, I was wondering, can't you rely on knowledge we have about dynamical systems? Could the measuring be evolving according to some differential equation, or could you use stochastic processes so that you don't have to invent many equations? Would that be a possibility?
Yes. Yes, I think yes. And we just started this study and it's a quite new one, and we are searching for some more direction to continue. So if you suggest this, why not?
Okay, are there any other questions or remarks or? Okay, so thank you one more time, Fatima. So I would like to invite the last speaker, Judith Sharpazasuji, with the title The Application of the Choquet Integral in Fuzzy Cognitive Maps. So stage is yours.
Thank you. Good evening. My name is Sharpazasuji Judith, and I'm a PhD student at the University of Novi Sad. And together with my colleagues and supervisors, we are working on the application of the Choquet integral in fuzzy cognitive maps. I would like to talk about our motivation first. The complex systems are characterized by nonlinear behavior, uncertainty, feedback loops, and interactions effects among components. And traditional models like fuzzy cognitive maps, for example, rely on additive aggregation. And additive aggregation assumes independence between influencing factors. But in the real world complexities, there are synergies or redundancies or trade-offs. And therefore, we try to make an extension to fuzzy cognitive maps by replacing traditional additive aggregation, Choquet integral-based mechanism. First of all, I would like to recall the definition that we used in our work. Fuzzy cognitive maps are graph-based models which can model complex systems. In that graph, the nodes are the concepts in the from the system, and the edge. Pardon. And the edges between the nodes represent the influence between the concepts. As you can see, this is a number from the interval -1 to 1 that shows us a direction and intensity of influence. Fuzzy cognitive maps are represents dynamic systems. So if we give at time t activation levels to the concepts, then we are able to calculate the activation level of concepts in the next time step, t plus 1. Here you can see the original formulation of that. This is the formula. How can we calculate the activation level of concept Cj at time step t plus 1 with activation level of time t? And we need a function, which is a monotone transfer function, for example, a sigmoid function for that aggregation. In our work, we try to replace that part of the activation rule with a Choquet-based method. therefore, we need a definition of a fuzzy measure and the Choquet integral. Of course, today we heard twice this definition, so I just recall. So fuzzy cognitive, we use the classical definition of fuzzy cognitive measures, which is important to us that we are not required to be additive, because we use this for describing synergies and redundancies and trade-offs. And if we have a fuzzy measure, then with input vector, we can define Choquet integral, discrete Choquet integral, as you can see in a classical way. Okay, we were using two additive fuzzy measures because we thought that these fuzzy measures gives us a middle ground between additive models and the fully non-additive measures, because this two additive fuzzy measure keeps us the semantics of fuzzy cognitive maps, and the pairwise interactions are intuitive to understand and to visualize. And of course, we keep the number of parameters manageable compared to the general fuzzy measures. And after the definitions, I would like to introduce our ideas about our model. How I said before applying the Choquet integral, we must to define an aggregation inputs. First of all, we defined the influencer set. For the fixed target concept CJ, we identified a set of all concepts exerting a direct causal influence, as you can see. With this set, we can define a non-negative input vector for this Choquet integral with multiplying the absolute weights, okay, with activation of concepts in time t. And the most yes, thank you. Part of our work is to give a formula how to express the fuzzy measure of singletons and the two-element sets, just relying on the edges, divides of fuzzy cognitive maps. For definition, first of all, I would like to show you the definition of singleton measures here. For each concept Cj, the singleton measure mu j or I calculated by normalizing the absolute weight of the incoming edge from Ci, as you can see. And our model for calculating the fuzzy measure of two-element sets, which we need for the two additive fuzzy measure, you can see here. It is calculated by summing the individual importances and adding an interaction term, which is calculated from internal causal relations among the influencing concepts. We have to make a little correction step because it can, if this interaction is negative, then to ensure the monotonicity of the fuzzy measure, we have to make this little correction step. And of course, here is the classical definition of two-element fuzzy measure, how we calculate the sets which has more than two elements. This is a classical formula from the literature. And after that, we have the input vector. We define the two additive fuzzy measure, and therefore we can calculate the Choquet integral. And for now we use the classical sigmoid function in that step. And this was our idea to replace the additive part of the additive part in the formula. And I would like you to a little example how it works. This is a small fuzzy cognitive map with 4 key concepts. As you can see, C1 is fiscal austerity, C2 is a social support, C3 is institutional capacity, and C4 is quality of policy decisions. We have 3 directed influence on concept C4, and which is very important for us. There are 3 internal interactions between C1, C3 and C2, C3. There is a synergy, and between C1 and C2 there is a trade-off. We need an activation level. We were working with the T nulla time step, and there is an activation level at time T nulla. The C1 concept is on a high intensity, as you can see. The C2 concept is moderate, as you can see, and the C3 is low, as you can see. And now we are going to define a fuzzy measure and to compute the Choquet integral. Okay. We need an input vector. We calculate the input vector at time T nulla for concept C4, as we defined earlier. And here you can see the calculation and the final vector, final input vector. Okay, then we need a fuzzy measure. First of all, we calculate the fuzzy measure for singletons. As you can see, the fuzzy measure for concept C1, C2, and C3 with a given formula, we got these numbers. And of course, the interpretation told us that the highest individual importance is institutional. Okay, and after that, we calculated the fuzzy measure of 2 element sets. First of all, we calculated the interaction numbers, as you can see, and with these numbers, used the given formula and and got 3 numbers for fuzzy measures. And of course, now we have fuzzy measures and input vector to a Choquet integral. And with these numbers, input vector and fuzzy measures we need, we can calculate and get the aggregated value with non-additive aggregation. And what is exciting, we use the standard sigmoid function and give final activation for C4 concept in time step 1. And with classical additive model, we get a high activation level. And with our model, we get moderate activation, which can tell us that we capture the trade-off between the concepts. And what is our future plans? Of course, we have to analyze the dynamic properties like convergence, stability conditions, circle analysis under various transfer functions. We used only sigmoid function for now. Of course, we have to apply. We want to make an application in a real world case and to validate the modeling of synergic effects. We are going to try data-driven or hybrid learning algorithms for fuzzy measures. And of course, we have to make a quantitative analysis to compare the classical fuzzy cognitive maps with our new fuzzy cognitive map representation. And this is our idea for now. If you have any question or suggestion, please tell me or ask my colleagues, Marta. Thank you.
So are there any questions or comments for this presentation? If no, thank you one more time, Judith.
Thank you.